All right, guys, number one of our test review for the solids, liquids, enthalpy, and specific heat. Now, on this one, on number one, it says the phase diagram for a pure substance is given below. Now, whenever we look at a phase diagram, it is involving pressure in atmospheres and temperature in Kelvin. And what we see is see the three states of matter. So we see a solid, we see a liquid, and we see a vapor state of matter. Okay. Now, from this graph, we can determine a lot of things. The first thing we can determine is melting points and boiling points. And on this graph, it doesn't really represent it very well, but normal atmospheric pressure, which is 1 atmosphere, will be our normal boiling point. So we would basically go up to 1, which would be way down here. And as we moved across and it hit one of these lines, that would tell us what it's doing. If it hits a line going from a solid to a liquid, obviously we're melting. If it's moving and hits the line going from a liquid into a vapor, we know that it is boiling. Okay. Now, other points about the graph, we can also tell way down here, this point right there is called the triple point. Now, the triple point is where solid, liquid, and gas all exist in equilibrium. They all exist together at that point, which is that pressure and that temperature. So looking at this graph, the triple point would be 50 atmospheres and 200 Kelvin would be the triple point. The other point that we have is called the critical point. It's way up here. Okay, the critical point is where we see that we have the critical temperature, which is 400, and we have the critical pressure, which is 200 atmospheres. And it's the point at which nothing can exist in a liquid state. Okay, that's our critical point with our critical pressure, critical temperature. Okay, so in this question it says what is the lowest temperature at which liquid can exist. So here's the liquid state of matter, and basically we just move down to the point where, well, it can't exist past 200 Kelvin. Okay, so 200 Kelvin is the temperature at which, if it moves any more this way, on that scale, that temperature, if it's anything below 200, then we know that it cannot exist in a liquid state. All right, moving on to number 3. It says the phase diagram for a pure substance is below. We see that now they've labeled the solid, the liquid, and the vapor state. And it says what is the critical temperature? Okay, well, the critical point is right here. Okay, so we look down and we see what is the critical temperature. Well, the critical temperature is going to be 400 Kelvin. All right, moving on to number 7. And in number 7, it says the surface tension describes, and basically it wants the definition of the surface tension. And the correct answer would be number 2. It is the inward force that must be overcome in order to expand the surface area of a liquid. Basically, what happens with surface tension is that if you think of, let's think of water molecules. Okay, if we think that we have a positive end and a negative end because it's polar. Okay, what happens is that water molecules will line up around each other, and the water molecules that are on the inside that are able to line up have all of their positives and negatives surrounding each other, and they interact with each other within the liquid. But the molecules that are on the very top can only react and only be pulled in by the ones on the bottom because there's nothing above it. So therefore, what happens when we have our surface tension is that these molecules that have these charges on the outside, they all get pulled in towards the middle because they all want to, the only thing they have to react with is the stuff in the middle. So basically what happens, because of the surface tension, it's just that force that pulls everything together. This is how when you get water and water comes close to each other, they will pull together to make one drop of water instead of having multiple drops just rolling around. They pull together. And it's because of this surface tension, that inward force that pulls those molecules. Okay, moving on to number 9. It says viscosity usually increases with the increasing in temperature. Now, the definition of viscosity is the measure of a liquid's resistance to flow. Okay, the main example that we usually use for this is we talk about molasses or syrup. If syrup is very cold, it moves at a very slow pace. But if we heat up the syrup and get it hot, it moves at a greater rate. Okay, so in general, what we see is viscosity is inverse to temperature. So as we increase the temperature, it flows easily, so it has a very low viscosity. If we decrease temperature, it moves very slow, so therefore it has a higher viscosity. So the answer to this question would be false. Viscosity usually decreases, that's what it should be, with the increase in temperature. Now, moving on to number 11, it says, which contains more molecules of water? 5.96 times 10 to the third, which we can, not times 10 to the third, but 5.96 cubic centimeters, which we can change to milliliters, because remember they mean the same thing, of ice at 0 degrees Celsius, or 5.96 milliliters of liquid water at 0 degrees Celsius, and which contains more molecules. Now, this problem is basically asking us to think about density. It gives us the density of ice right here. And one special characteristic of water is that water is actually less dense in the solid state than it is in the liquid state. This gives water, the when it's in the solid state, the ability to float. So ice floats in water. So therefore, that water is actually more dense. So which contains more molecules? What we would see is that the liquid would contain more molecules because the liquid is actually more dense than the ice. Okay, moving on to number 13, it says choose a state of water in which the water molecules are farthest apart on average. So what we're trying to figure out is where are the water molecules in each state of matter. Now when we're looking at this, we know that water has a special property that the solid state is actually less dense than the liquid state, so they would be farther apart in the solid state than a liquid, but we see that we have vapor here, or steam, which we know that the gaseous state. Now all gases, remember that their molecules are extremely far apart, so if we're looking at all of these, we know that in steam, in the gas state, would be the farthest apart on average of all the molecules. Okay, moving on to number 15, it says determine the specific heat of a material if 39.7 gram sample absorbed 44.2 joules as it was heated from 293 Kelvin to 304 Kelvin. Now in this problem, we see that we have our equation Q equals MC delta T, and I know that I'm using this one because it specifically asks for specific heat. Okay, so when I'm using this equation, I am solving for my specific heat, or my C value. So therefore, how do I do that? Well, I divide both sides by M delta T, and I get my equation that I'll be using where I have specific heat equals my Q over M delta T. Okay, so I go ahead and I look at what I have. Now here I see I have 39.7 grams sample, so that would be obviously my mass. And I have 44.2 joules. Joules is obviously energy, or heat energy, which is always Q. And then I have two temperatures. Now remember that that triangle means change in temperature, or final minus initial. So I know that the first one that I see is going to be my temperature initial, and the second one I see is going to be my temperature final, unless they state otherwise. And in this case, they don't. So from here, all I have to do is plug it in. I have my 44.2 joules, all divided by my mass, which is 39.7 grams, multiplied by my change in temperature, which is going to be 304 minus 293, and close everything off, and go ahead and plug that into a calculator. And what I would see my answer to be is I would get a very low specific heat, or a C value of 0.0977, and that unit would be joules, grams, Kelvin. Okay, moving on to number 17. Now in number 17, it's part 2 of 2, so we're going to be using some of 16's answers in number 17. And it says, how much energy will the same sample lose if it's cooled from 46 to 23? Now, what we have here is we have our equation where we have Q equals MC delta T. because I'm searching for energy, and energy is Q, so it's already set up for me. So the only thing that I need is I need a mass, I need a specific heat, and I need a change in temperature. Which what we would get for this, we would look in 16 and we would figure out our mass because it's the same sample, so it has the same mass. So we have 60 gram sample from our first part in 16. And also, what we did in 16 was we solved for the specific heat. So now I have a specific heat for that sample, which is 0.2847, and that would be joules, grams, Kelvin. And then I have a change in temperature, which I'm multiplying all this together. I just ran out of room over here. So I'm multiplying that all together, which are our final minus our initial, which our initial temperature is the first one that we see, which is 46, minus my 23. Okay. Now I am going to get a negative number here, but since in the problem it says that how much energy will it lose, it's already telling me that it's losing the energy, so all it wants is the magnitude of it, which magnitude means it just wants the number. So no positive or negative, it just wants the number. So when I plug all this into my calculator, I see that I get an answer of 392.84 joules, and it would actually be negative because of this value, but what I would actually plug into the computer is the magnitude, which would just be that number right there. All right, moving on to number 19. Now, in number 19, it's asking us to calculate the enthalpy change for the reaction. Now, remember that the enthalpy change, that's the equation where we use the delta H, or the change in our enthalpy, equals the delta H of our products minus the delta H of our reactants. Okay, we're using this equation. Now, what we have to look for is in this problem, it has to give us the heat of formation, which that delta F right there, that's what it means. That is the heat of formation. And what we'll do is we'll multiply it by the coefficients in front of the compounds, or in front of the molecules, and then we'll add the products together, add the reactants together, and then subtract. So all we're doing here is we're multiplying, we're adding, and we're subtracting. Okay, so the first thing we have to do is we have to multiply by the coefficient. Now we have to make sure that our equation is balanced. So we have one lead, we have two oxygens, we have two oxygens, we have one carbon, we have one carbon. So it's already had and it's balanced for us. So we know that the coefficients in front are going to be 1, 1, 1, and 1. So then all we have to do is multiply them by their heat of formations. So I'm going to multiply my lead oxide heat of formation by 1, which that will give me negative 217.3 kilojoules. Because our unit here is kilojoules per mole, but we're multiplying it by 1 mole and we just get kilojoules. And that is for my lead 2 oxide. Okay. Now, the next one that we have is carbon monoxide. So it is a 1, and we're going to add these together because they're both reactants. So 1 times my 110.5 kilojoules. Okay, and then we come over here and we see that we have lead. Now the only thing we have to remember is the heat of formation for any element is always 0. So this is just going to be 1 times 0, which is 0. Okay, so our only product that we're going to have is carbon dioxide, which we have 1 times its value, which is negative 393.5 kilojoules. Okay, so we went ahead and we multiplied. Now what we need to do is we need to add these two together, and then we will subtract. So what we're going to end up with is our enthalpy, or our change in enthalpy, delta H, is going to equal our products, which is negative 393.5 kilojoules, minus, and remember that that's negative as well, forgot to write that, minus our negative 217.3 plus negative 110.5 kilojoules. Now, realize that when we add these together, we're going to get a negative number. And whenever we subtract a negative number, what we're actually going to end up doing is we're going to be adding. So we'll have our negative 393.5 plus the sum of those two, which would give us a change in enthalpy of right around negative 65.7 kilojoules. Now, what this means, remember that if we have a negative value for our enthalpy change, that means it's going to be exothermic. It's giving off heat to the surroundings. If it was positive, we know it would be endothermic. It would be taking heat from the surroundings.